complexity, there is this constant to swallow, and various people have...
it's large compared to the number of fingers, but small compared to Avogadro's number. So these people who do cosmology shouldn't get indigestion from it.
Okay. So anyway, so sorry I have changed the notation, but too much in the last minute, and I forgot about the indexed version. So I would like to call this complexity C of x for reasons that come clearer later. So there are two interesting facts about this complexity. One of them is that the upper bound is just the length of the string, right? Because you can always give the machine the instruction, just print out this. So the constant is the instruction that tells the machine to print out this, right? So the lower bound is a little more interesting, but it's also simple. Lower bound, there is a kind of statistical lower bound, right? So for each k, right, how many strings can there be whose complexity is less than n minus k? There can be at most 2 to the n minus k, because simply there are no more descriptions than 2 to the n minus k. Well, here you added up all the shorter descriptions, but and that is actually, that shows that really, right, only if you want to have a, so the number of strings whose description is by 10 smaller than the maximum is already the fraction of those is only 1 over 1,000, right, and 1 over 2 to the 10. So really, most strings, by far most strings have near maximum complexity. So this is already some indication that complexity can be viewed as a kind of measure of randomness. So most strings are random. There are other, and I will not go into it too much, why this is a good measure of randomness. We'll see something. So, but notice it's a peculiar proof, right? It's really very much an existence proof. I didn't show you any example of a string whose complexity is larger than even 100. And that's not accidental. Nobody can show you such a string, well, with a proof. So, so I will not...
So the catch, so what's hard to prove is that maybe there's some way its complexity is lower than 100?
No. Well, here is a... I will not show you exactly that, but essentially we'll show you right on this page. So, so I will show you right away a proof of uncomputability. Right? Namely, I will show you that this function, the complexity function itself, is an uncomputable function. Okay, but it's really but the same proof actually will show you that there is no it's not just uncomputable, but there is simply no non-trivial computable lower bound for it. Right? So so why? So that the proof is going back to using an old paradox, right? The paradox is what I forgot whose paradox it is, but
one form of this Berry's paradox.
Berry's, yeah. So right. So what I mean, there are some numbers clearly that can be defined with a few words, right? I say with less than 100 words, like this one. The first number that begins with 100 nines. Right, that was defined with a very few words, right? But there certainly there is some first number that cannot be defined with 100 words, right? But I just defined it. So that's a paradox. This is a paradox, but
shorter than 100 words or 100 characters or something like that. Yeah.
Yeah, whatever characters, yeah. So I think in this case it is more, well, maybe I should say words, yeah. words that can be found in the dictionary, right? Okay, so so now this is a paradox, but it just it depends on this paradox depends on the vagueness of what it means to be to define something, right? Now, so let's make it more precise. So let us say that P defines X if U of P is equal to X. So right, if P is a description of X in our sense, right? Now, if C is computable, right, then it means that there would be an algorithm, let's call it Q, which on input K just outputs the first string that is not definable, that has complexity larger than K, that has no description smaller than K, right? And then let Q be the length of the program of this algorithm, right? Then, so now we can write a program of R of K that will just output this first number X of K, which has larger description, right? Only large descriptions, right? Now let's see what is the length of this program R of K, right? Well, we had to give this Q the length of this program. Plus, I had to give the number K that takes log K bits, right? Plus, I need some more instructions to just tie all this together. That has some length P, constant. So the total length of R of K is P plus Q plus log K, right? But you know, when K is large, this is definitely less than K, which is a paradox, because now I just gave a program for outputting a number with larger I just gave a description which is less than K, and it outputs a string with description complexity larger than K, right? So, okay.
So instead of proving that definability is a vague notion, it proves that the Kolmogorov complexity is an uncomputable function.
Yeah, yeah. So, yeah, so this is a contradiction.
There's no algorithm.
Okay, so the point is, anyway, so the reason I brought this proof up is to show that, to show at least something tangible, a tangible and simple mathematical proof of something being uncomputable, right? So now you see something. Yeah.
That the complexity function is uncomputable?
This proves that the complexity function is uncomputable because we assumed it's computable, and we are led to a contradiction.
And this complexity function describes the complexity, right?
Yeah, it describes
I'm making a lecture about complexity.
See?
But you're making a lecture about complexity, and you define complexity.
It's definable but uncomputable.
I defined it, but I defined it, but it's not computable. It's not computable in terms of by any of our computation, by all our equivalent computation models. Like there is no tuning machine that can compute it.
So you cannot compare the complexities of two algorithms because you cannot.
No, you cannot. Well, you can compare it in in theories, right? Theory, but I mean you cannot. Yeah, you cannot compare. Well, first of all, complexity of algorithms. So. Again, the main reason I am giving this talk is because Charlie thought that many physicists cannot distinguish between computational and description complexity. Those are two different things.
He's talking about description complexity.
I'm talking about description complexity.
So computational would be how much time?
We are getting to that. We are getting to that.
This is the less familiar kind of complexity.
Okay.
Well, for some people this is the more familiar one, others the.
So I have a specific example in my mind. I have a fractal, where it's very easy. You know, with fractals, you can give the rules very simply, right?
Like the Mandelbrot set.
Yeah.
Well, you must be careful. So actually, actually, it turns out That's quite a subtle question. It turns out that the boundary of some of these Mandelbrot or Julia sets are actually uncomputable.
Okay.
So, but there,
how to create it. So
yes, how to create it. But when first of all, it brings up a more difficult question of computability when real numbers are involved, or complex numbers are involved. But the point is that it's one thing to generate it, but it's another thing is trying to decide about the point whether it belongs to it or not. Those are again two different questions.
Some of these sets, you can generate them in the limit of an infinite process, but to say whether that process ever meets a particular point could be uncomputable, even though the generating process is
exactly.
entirely computable.
Yeah, so
the description of the Mandelbrot set, right, will not output the Mandelbrot set.
No, that's what.
yeah, it's a definition. Some of these mathematics. We are talking about at the very low end of the hierarchy of mathematical definitions, essentially using a single quantifier. Now, how about using 2 or 3 or 5? Right? Then you are even much farther. We are talking about notion. Well, for example, even if you define what it means for a sequence to have a limit at a certain point, right? That involves already 3 consecutive quantifiers. Generally, you cannot computationally check whether a certain sequence is actually converges to a certain point.
Even though you have a measure there, which, okay, so I know it's just the words that much, but once I had a course in complexity in physics, and we talk about the fractals and the Hausdorff dimensions, right? And I asked, okay, so you compute these Hausdorff dimensions, what do they represent to you? The professor said, good question, it represents the complexity.
Well, whatever, again, complexity is a word applied to a lot of different things. Yeah. For any theoretically defined set, one can compute, one might compute the Hausdorff dimension, right? For example, for the Cantor set, we know it is log 2 of 3, right? So, or log 3 of 3, 3 or 2, whatever. I forget. Log 3 of 2, but log base 3 of 2. Anyway, so one can compute it, but it doesn't mean that if you are given in something, an infinite object by some definition, then you necessarily can
wouldn't that be a measure?
Please.
Okay.
Yeah. Okay. So now let's jump to the other notions of complexity, right? Computational complexity. So I would prefer to call it a cost of computation to distinguish, right? So let us say on a universal machine, right? You could define. You could say the time of a program on input X would be just the number of steps this machine makes, right? But this is also seems a much less invariant notion than the Kolmogorov complexity, because it depends a lot on what machine model we are using. For example, a lot of people would view a one-tape Turing machine as quite unreasonable. You cannot. If on a 2-tape Turing machine, at least you can check the equality of 2 strings in linear time. On a 1-tape Turing machine, not to take quadratic time, you have to go back and forth. So you don't, and then a number of other things like this. So it looks kind of unreasonable to define this notion, or quite machine dependent. But and also cost of computation. Why time? Maybe memory, amount of memory used is more important. In many cases, it is more important. Why not some combined quantity of these or some again other things? And indeed, this is all reasonable, good questions, and especially the relation between time and storage is very subtle, and we'll talk about it a little later. But it is, at least it turns out that when you are coarse graining enough, then you can ask then things become a little more invariant. So for example, all the reasonable machine models do simulate each other within polynomial time. So a Turing machine simulates a cellular automaton even in polynomial time, and of course vice versa. And
So
Kind of the definition of a reasonable model, right?
yeah, that's a well. Yeah, so no, I wanted to say that yeah, it's an issue, and especially an issue, right? When then do you include quantum computers in that? Then no, but somehow what we are excluding here are, let us say again, theoretically, at least. No, you could exclude a lot more, but at least among what you consider machine models, I would want to exclude those models which are massively parallel in the sense that, let us say, in each step, each component can give birth to another component, and so this way the machine can double its size in each step, right? Because that kind of massive parallelism is really leading to a different notion of complexity.